So now we are going to finish up the chapter 12 notes, and we're talking right now about equilibrium vapor pressure. I'm going to define it first and then explain probably how it's measured, then finish up the slide. So let me first define it. Equilibrium vapor pressure is the vapor pressure measured when dynamic equilibrium exists between condensation and equilibrium. That's a lot of words, so it's probably easier if I just kind of show you an example or show you how it's measured first. It's actually in the next slide, but um, first of all, if you had some sort of liquid, let's say water, H2O liquid, evaporates into H2O gas. So if you had a cup of water out, it will start evaporating, and over time, eventually that cup of water will disappear because it will have evaporated. But if it's in a bottle, a sealed container, it's actually technically evaporating, but the amount of water in it stays constant is because um, it also condenses back. Meaning, let's say here, let's say you put some water first of all, it's just sealed, so there's nothing above it, just air or whatever, and it starts to evaporate. So it starts evaporating, turns into a gas. Well, this gas eventually also turns back into a liquid, condenses, but and it condenses, but is also evaporating. It gets to a point where it is condensing, it is evaporating, but the rate of evaporation remains constant. How fast is it turning from a liquid into a gas? How fast is it turning a liquid into a gas? It stays the same the entire time. But eventually, it starts condensing. There are gases in here that will turn back into a liquid. So the rate of condensation increases over time. Eventually, you get to a point where how fast it condenses is equal to how fast it evaporates. So how fast it condenses is just as quickly as it evaporates. That's what's happening in a water bottle if you just leave it out for a long time. It doesn't even take a long time, but after a while, yes, water is evaporating, but it condenses. It evaporates, condenses. It's happening at equal rates. I think next chapter, chapter 13 or 14, one of them is actually about equilibrium. That's actually, I think it's chapter 15. But it's when the rate of one thing is equal to the rate of its opposite. Okay. Well, the equilibrium vapor pressure is the vapor pressure measured when this dynamic equilibrium exists. Dynamic meaning it's always occurring. It's evaporating, it's condensing, just at equal rates between condensation and equilibrium. So it's evaporating, it's condensing. Well, that means there's a gas in here. How much gas? I don't know, but the pressure of that gas at equilibrium is called the equilibrium vapor pressure. As you can kind of guess, as you increase the temperature, the equilibrium vapor pressure will increase. As you decrease the temperature, the equilibrium vapor pressure will decrease. But in general, the definition of equilibrium vapor pressure is the pressure of the gas when equilibrium is reached between condensation and evaporation. So it's condensing, it's evaporating, condensing is evaporating at equal rates. When that happens, what is the pressure of the gas? That is equilibrium vapor pressure. Okay, that's the definition of it. We need to know that because we need to use that for definition of what is defined as boiling. Okay, so this is before evaporation, this is at equilibrium. Once you're at equilibrium, the pressure of the gas at equilibrium is the equilibrium vapor pressure. Okay, we're going to skip the next slide, so ignore that for right now. Okay, boiling points. The boiling point is the temperature at which the equilibrium vapor pressure of a liquid is equal to the external pressure. External pressure means, okay, if we're talking about, say, just in a regular room, what is the pressure in the room? If you remember back in chapter 5, like standard temperature and pressure, I don't care about temperature, okay, just what is standard pressure? What's the pressure in a room at sea level? If you remember, that is 1 atmosphere, or which is 760 millimeters mercury, or 101.3 kilopascals. Let's stick with atmospheres. It's measured at 1 atmosphere. Oops. At the bottom, well, once if a thing disappears. Okay, so it's measured at 1 atmosphere at the bottom. So boiling point is when the equilibrium vapor pressure is equal to the outside or external pressure. So we're usually talking about your normal boiling point, which is at 1 atmosphere. The normal boiling point is temperature at which a liquid boils at 1 atmosphere. But we could be boiling water not on the surface of the earth. We could be boiling water at different pressures. But we're talking about like on the surface of the earth. On the surface of the earth, the pressure is 1 atmosphere. So what does that mean? Let me go back to the slide about the picture with equilibrium vapor pressure right here. So at equilibrium, when it turns from a liquid to a gas and it turns gas back into a liquid, that is equilibrium vapor pressure. And the pressure of this gas, that is defined as equilibrium vapor pressure. But when this equilibrium vapor pressure is equal to 1 atmosphere, that means it turns into a gas as easily as it turns back into a liquid. So that is the definition of boiling. Because what's really happening when you're boiling? When you're boiling, what you're doing is you are turning this liquid, it heats it up, and you're increasing the equilibrium vapor pressure. You heat it up, let's say you have water is 50 degrees, let's stick with Celsius. It's 50 degrees Celsius. You're increasing the equilibrium vapor pressure, but the pressure in the surrounding pushes the water or the equilibrium, it can't turn into a gas because the outside pressure is 1 atmosphere. At 50 degrees Celsius, it doesn't want to turn to gas. But once you get to, say, 90 degrees Celsius, it really wants to turn into a gas. At 90 degrees Celsius, it really wants to turn to gas. It increases the vapor pressure even more. But still, the outside air is pushing it down so much that it doesn't want to turn into a gas. But eventually you get to a point, and it's 100 degrees Celsius for water, where the equilibrium vapor pressure, the pressure of this liquid turning into a gas, is equal to the air pushing it down. At that point now, at least at sea level, it can start turning into a gas. So for water, that happens to be at 100 degrees Celsius. Of course, you know, the boiling point of different substances differ. So ethanol, alcohol, boils at 78.3 degrees Celsius. Other things like the gas argon boils at negative 186 degrees Celsius. So these are not numbers you ever memorize, though you should know water boils at 100 degrees Celsius. Okay, but normal boiling temperature is the temperature which a liquid boils at 1 atmosphere. Boiling temperature, or boiling point, is temperature at which the equilibrium vapor pressure is equal to the outside or external pressure. Okay, two other terms, critical temperature and critical pressure. Critical temperature is a temperature above which a gas cannot be made into liquid or made to liquefy no matter how great the applied pressure. So if we increase the pressure, of course, the boiling temperature will increase. In fact, that's how a pressure cooker works. Or I was using an Instant Pot the other day to cook, which is a type of pressure cooker, electric pressure cooker. A pressure cooker increases the pressure inside the pot. As you increase the pressure, if the external pressures increase, the equilibrium vapor pressure will have to be higher. So inside a pressure cooker, it cooks at higher temperatures. And since it's at higher temperatures, it also makes your food cook faster. But there is a point that above a certain temperature, it cannot be made to a gas no matter how great the pressure. Imagine you had some sort of container which you had some sort of pressure container which you can increase the pressure, well, infinitely, okay, it's infinitely strong. Well, above a certain temperature, if it's in a gas state, it cannot turn into a liquid, no matter how great the pressure. For water, that critical temperature so happens to be 374.4 degrees Celsius. So above this temperature, 374.4, and not numbers you memorize, a gas cannot be turned into a liquid, no matter how great the pressure is. So it cannot be made into a turned back into a liquid, no matter how great the pressure. If you happen to be at the critical temperature, 374.4 degrees Celsius, it can turn into back into liquid at a certain pressure. That pressure is called the critical pressure. Critical pressure, the minimum pressure that must be applied to bring about liquefaction or turn into liquid at specifically its critical temperature. Okay, so these are just two definitions. So our phase changes, you can go, of course, solids to liquids to gases, and we're not going to even talk about plasmas or anything like that right now. Just stick with our main three states of matter, solid, liquid, gases. As you should know, if you go from a solid to liquid, you're talking about melting. Ice, solid ice, turn into liquid water, you're melting it. The opposite of that is freezing. Liquid to solid is freezing. So solid ice into water is melting. Water into solid ice is freezing. The melting point or the freezing point, they're technically the same temperature. Ice melts at 0 degrees Celsius. Water freezes at 0 degrees Celsius. By the way, we're assuming less at regular pressure right now. So let's assume we're at sea level. So the melting point of a solid or freezing point of a liquid is the temperature at which a solid and liquid phases coexist at equilibrium. So if it's at 0 degrees Celsius, you can have, basically it could be a solid ice, it could be liquid water, it could be either one at the same time. Okay, molar heat of fusion, the energy required to melt 1 mole of a solid substance. So let's say you had 1 mole of, 1 mole of water. We got 1 mole or say ice. 1 mole of ice at 0 degrees Celsius. If you have 1 mole of ice at 0 degrees Celsius, well, ice can stay solid at 0 degrees Celsius. Water can freeze at 0 degrees Celsius. Well, how much energy do we need to melt 1 mole of ice at exactly 0 degrees Celsius? That's called the molar heat of fusion. And to melt 1 mole of ice at 0 degrees Celsius, it takes 6.01 kilojoules of heat to melt 1 mole of ice at 0 degrees Celsius at its melting point or freezing point, same thing. Of course, heat of fusion depends on the substance. Alcohol, which will melt or freeze at negative 117 degrees Celsius, it will take 7.61 kilojoules of heat to melt 1 mole of, it's not ice, of solid alcohol, ethanol, at its freezing temperature, which is negative 117.3 degrees Celsius. I did not know that number before, and so I just see it right now. Okay, so if you had solid ice, and it's a negative 10 degrees Celsius, bring it up, negative 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. At 0 degrees Celsius, your ice can start melting, but it doesn't melt because it needs energy. So as we're heating up ice from, say, negative 10, negative 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, once you get to 0 degrees Celsius, it can start melting, but it still needs energy, so it takes time if you're heating it up, and it takes 6.01 kilojoules of energy per mole of ice to finally turn it into liquid water. Then as you heat this thing up, it'll still increase from 0 degrees Celsius, 1, 2, 3, all the way up to the boiling temperature water. And boiling temperature water, as you know, is 100 degrees Celsius. And from there, it takes energy to turn it from liquid water into gaseous water or steam. Okay. In fact, talking about into gas state, solid to a gas state, if you go from a solid to a gas without ever turning into a liquid, it's called sublimation. The opposite of that is deposition. Sublimation examples of that would be dry ice. If you had dry ice, it goes from solid state to gas state. Another example of that, just even your ice in your freezer. If you ever have ice in your freezer for a long time, like I don't use much ice, especially in the wintertime, and I see ice cubes in the freezer, and over time you probably notice it starts shrinking and shrinking and shrinking. Where does it go? It did not melt and then turn to gas. It went through a process of sublimation, went from a solid to a gas without ever turning into a liquid. The opposite of that, a gas turning to solid without ever becoming a liquid, is called deposition. Example of that is like if I took out a tub of ice cream from the freezer. I see on it within, few seconds, ice crystals are forming all around the sides of the ice cream container. It did not take gaseous water and air turned to liquid and the liquid froze. It was ice that is in the air turned into a solid ice, water that's in the air turned into solid ice, and it forms crystals against the side of the container called deposition. So a solid to a gas is sublimation. A gas to a solid is called deposition. Amount of energy to do that, heat of sublimation. Okay, we don't need to know that bottom part right now. The heat of sublimation, energy takes to sublime 1 mole of a solid. We don't need to know that right now. Okay, so last thing, phase diagrams. Phase diagram summarizes conditions at temperatures at which a solid, liquid, and gas can be. So this is phase diagram of water. It tells us x-axis temperature, y-axis pressure. So you should just know how to read a phase diagram. It's actually kind of simple, as you can, well, I know how to read graphs. X-axis temperature, y-axis pressure. So you can see that, hey, if you had a substance, let's say at 1 atmosphere and 50 degrees, here's 0 degrees Celsius and 100 degrees Celsius, 50 would be in the middle. If you had H2O at 1 atmosphere, 50 degrees Celsius, as you probably know, it's a liquid. If you had H2O, because it's a water, H2O 100 degrees Celsius and say half an atmosphere, it will be in a gas state or vapor. So learning how to read this is called a phase diagram. Notice there is a point in which solid, liquid, and gases all meet. It's also known as the triple point. The triple point. Notice there's also the dividing line between solid and liquid. That is the freezing or melting point. And dividing line between liquid and gases, or the boiling point. And a boiling point will change as the temperature changes. This is of carbon dioxide. Its freezing, melting temperatures, boiling temperatures all vary. But it does have the same or specific triple point, the point at which it goes from a solid, it could be a solid, liquid, or gas. And for carbon dioxide, it's a negative 57 degrees Celsius and 5.2 atmospheres. Okay, and that is all about this, and we'll go on from here.